Hey everybody, in this video, we will be diving straight into understanding the time temperature transformation, or TTT for short, or triple T for short, however you like to say it. Before we get started, we need to know the key concepts of what phase transformations are and why they matter. Phase diagrams show equilibrium conditions, but industrial production can't wait for equilibration times. This creates non-equilibrium conditions that engineers must understand and control. Now that we got that out of the way, let's talk about the real deal, the whole reason why TTT exists. TTT diagrams bridge the gap between theoretical phase diagrams and practical heat treatment by showing what actually happens during real cooling processes. Isn't that cool? It's like a manual you can refer without needing to worry about real-life factors. Of course, with the ability to do practical heat treatment, it opens up opportunities for practical applications as well. Most importantly, industrial relevance. Engineers especially use TTT diagrams to design exact cooling processes to achieve desired microstructures and mechanical properties.
So next, I'm going to talk about the eutectic points and the triple T diagram. So when you cool down the steel after 727 degrees Celsius line, all the austenites has to change. It can't hold on to the carbons anymore. And how fast we cool it down determines the final macrostructure. So the first key phase you need to know for the triple T diagram is austenite, which has a phase center cubic structure. And the second one is ferrite, which has a body center cubic structure. Thirdly, perlite. If we cool down the steel naturally or slowly, the carbon has plenty of time to organize, where it will form a zebra-like or fingerprint-like structure. Next, bainite. If we cool it down a bit fast, the carbon doesn't have time to make neat layers. It gets messy and forms needles or rod-like structures. Next, martensite. If we quench it instantly in water, the carbon gets trapped. It frees into a body-centered tetragonal structure, where we call it martensite. Finally, sphaerodite is produced by heating steel that has already formed perlite, bainite, or martensite structure to a temperature just below the eutectic temperature.
TTT diagrams are essential tools in material science, particularly in the study of phase transformations in steel. A TTT diagram represents the behavior of a material undergoing isothermal cooling. That is, it shows what happens when a material is rapidly cooled to a specific temperature and then held constant. Unlike continuous cooling curves, which reflect real-world cooling processes, TTT diagrams isolate the effects of temperature by maintaining it steady, allowing for precise observation of transformation kinetics. The diagram itself is composed of three key curves. First, the curve nearest to the left indicates the moment when a phase transformation begins. The dotted middle curve indicates the 50% transformation, which marks the point at which half of the transformation has occurred. Finally, the last curve shows when the transformation is fully finished. A particularly important feature of the TTT diagram is the so-called nose of the curve. This is the point where transformation occurs most rapidly, typically located around 540 degrees Celsius in the iron-carbon system. The nose serves as a critical boundary. Above it, perlite tends to form. Below it, bainite becomes the dominant phase. This distinction is vital for engineers seeking to tailor mechanical properties through heat treatment. By combining multiple S-curves at different temperatures into a single diagram, the TTT plot enables engineers to determine the exact timing and temperature conditions required to achieve desired microstructures. In doing so, it provides a powerful framework for controlling hardness, toughness, and other performance characteristics in steel. Therefore, the TTT diagram is not merely a chart, it is a roadmap for transformation, guiding metallurgists in the precise orchestration of thermal treatments to engineer materials with optimal properties.
Now I'll be talking about transformation products. The first one is perlite, where it is a phase that can be found above 540 degrees Celsius, and its structure is alternating layers of cementite and ferrite. It is split up into two types. One type is called perlite, where it forms at high temperatures of 700 degrees Celsius. There would be greater atomic fusion, which gives it thicker layers, lower strength, and high ductility.
Another type is fine perlite, which forms at lower temperatures of 600 to 700 degrees Celsius. There would be limited atomic diffusion, which creates finer layers that are stronger but more brittle. The next product is bainite, which forms at below 540 degrees Celsius. Its structure is fine cementite rods within ferrite strips. It is finer than perlite, so it is stronger than fine perlite. It also forms at moderate cooling rates. Moving on, martensite is formed from rapid quenching. It forms when cooling is so quick that it avoids all the TTT curves. It has a diffusionless transformation, which means that atoms only shift small distances. For martensite, the transformation is extremely fast and the percentage of martensite formed depends on the final temperature reached. Its applications are in high-strength tools and components.
Now, let us talk about heat treatment processes and how they connect to the time, temperature, transformation, or in short, TTT diagram. Firstly, quenching. This is a rapid cooling process designed to avoid the TTT curves entirely. By doing so, we are able to lock in 100% of the martensite, which is extremely hard. In fact, nitrogen cooling is often used to push the martensite content even higher. Next comes tempering. Here, we reheat the martensite so that it transforms into ferrite with extremely fine cementite particles. The result is a balance with high strength combined with adequate ductility. That's why in the steel industry, they often rely on the quenching and tempering sequences, which helps to produce durable components. Then we have annealing, in which we heat just below the eutectoid temperature around 700 degrees and hold it for 18 to 24 hours to produce spheroidite. This is the softest and most machinable structure, ideal when easy machinery is required. Lastly, normalizing. This involves controlled cooling to produce fine perlite, giving it a balance of strength and ductility. One industrial application of the TTT diagram is in steel making using hydrogen-based reduction. When steel is produced using hydrogen-based reduction, it still requires careful processing and heat treatment, and the TTT diagram remains vital for predicting how its microstructure evolves during cooling. Since hydrogen can affect its steel properties, including risks like embrittlement, understanding transformation kinetics through the TTT diagram helps metallurgists design treatments that enhances toughness and minimizes defects. Moreover, green steel production changes impurity levels due to reduced carbon input and different slag chemistry, which can shift transformation behavior, making it necessary to re-evaluate the TTT diagrams for steels created via hydrogen reduction. In short, the TTT diagram is more than a chart. It's a powerful tool that guides heat treatment and enables industries to tailor steel for everything.
Okay.
谢谢你 for watching.
What should we-
你好咯，你好的，
Nandre.
Andre,
Andre.
感謝。
感謝。
Wait. Sorry.
Next, bainite. If we cool it.
So far.
Lock in, bro.
Sorry.
High strength combined with adequate ductility. That's why. That's why the steel industry no. Because which can shift. We can make it necessary to be re-evaluate.
Wait. Restart the background. What? Oh, you want? What was the sentence?
No. Okay, start.
Bro.
Hey everybody! Wow. A TTT diagram.
Aniq, you make it smile a bit. You look like you got abused at home.
Why?
You look like you got abused at home.
Later I use AI.
I think it's important.
Yeah, your eyes look bigger than usual. No, but not in a.
Because
not in
Jayden is standing beside, then you compare, of course.
No.
Third. Now I'll be talking about transformation products.